Good evening, everyone. Welcome back to NPTEL live session. So today we are in week 10 session where we will be discussing all the basic concepts that have been covered so far, and we will wait for a few minutes for others to join. And if there is any question regarding whatever we have read so far in the past weeks, feel free to ask or put your question in the chat box. I'll be happy to answer that. So we will be shortly starting the session in 1 or 2 minutes. So thank you so much for joining. So topics that have to be covered today. So last lecture that has been stopped at offer reaction. So we will take it again into consideration. We'll talk about the offer process. We will talk about the nickel effect and the arise of signal Nata catalyst. Also, we will be talking about the applications, limitations, as well as advantages of it. Next, we will take up normal pressure polyethylene process. Next, we will be having the classification, as we have taken the classification of polyethylene molecules. So today we will be discussing polypropylene, where we have 5 types of it, so that we will consider, and based on the branching and the pattern that they are having, then we will be looking at the mechanism of Wigler-Natta process, followed by we will be talking about the single site Wigler-Natta catalyst. That means the homogeneous version of this one. And at last, we will be taking a brief summary of whatever the catalyst that we have said so far in case of polyethylene, polypropylene. And lastly, we will take up the assignment questions, which will help you to solve the problems that have been given in your assignment. So these are not exactly the same assignments, but they are more or less matching, so that you will be able to use the basic concepts that you're going to read today, and then you can apply it onto your questions. So without any further delay, we will start with offer reaction. I hope you have understood in the previous session. I'll just give a brief again over here. So first topic of our discussion is offer reaction. So we know that offer reaction is nothing but this alkylated ethylene and aluminium plus CH2 N-1 ethylene molecule, and the temperature conditions is 90 degree to 120 degrees Celsius and 100 bars of pressure, and this results into your a R2Al CH2, CH2, NH, which is your linear long chain aliphatic compound. It's a kind of your extended ethylene molecule. But corresponding to this one, we also have a competing reaction, which is de-elimination, corresponding to the long chain aliphatic compound formation. We have this side reaction also, where this particular group, because it is having, this is your alpha and this is your beta, and whenever there is a beta hydrogen, so it will tend to form your R2AlH, and that will release as this alkene moiety, and this will form as an aluminum hydride as a product, because it will give your thing back how this works. So you have a CH2, CH, one H I'm writing over here, and R dash. This is alpha and this is beta. Whatever is attached to the aluminium, that is alpha, then followed by its beta. So this hydride would go over here, and this bond will shift here, and it would release your CH double bond CH R dash, and hydride would be released at this product. So this is your side reaction. So during this process, Ziegler actually was the first one who observed an opposite trend, that instead of getting your proper aliphatic chain, we are getting, if we take two ethylene molecules, so it is undergoing dimerization to give you the butene molecule. So this they observed in quantitatively, we are getting it. So what could be the possible reason of not involving into long chain aliphatic compound, but to give and stop at 1-butene? So it was because they found that there was some nickel impurities, therefore called as nickel effect, because of which it is stopping at 1-butene and not going to further. Therefore, nickel effect was the source of invention of your Ziegler-Natta catalyst. Okay, so and what is that? So what they found that so what they were doing, they wanted to see that other transition metals, they are also giving this premature termination of a reaction similar to the nickel effect, and some unexpected observation was made. We got 1-butene over there. So it was found that TiCl4 in a combination of diethyl aluminum chloride that produced high density polyethylene molecule at extremely low pressures of just 1 bar. So this particular system is known as your Ziegler-Natta system, which is taking an ethylene molecule and producing a high density polyethylene, which the classification we have already read, and reaction goes in this particular manner. We have taken N molecules of ethylene, and in presence of the Ziegler-Natta catalyst, titanium tetrachloride, diethylene aluminum chloride, 25 degrees is room temperature, and 1 bar of pressure, extremely low, I would say like ambient conditions. So it is producing your polyethylene, and this polyethylene is linear It is a high density polyethylene. Also, it is having a molar mass of 10 to the power 4 to 10 to the power 5 dpi. So this was given by Ziegler in 1955. I hope you're getting my point. So earlier we were getting a long chain aliphatic compounds, but from the alpha reaction, and there was a side reaction where it is getting de-illumination because it is forming an aluminum hydride. In uh, investigation of this kind of process, Ziegler found that when we are taking an ethylene molecule, it is stopping at one butene kind of system because of the nickel impurities. That means there is an effect of 3D transition metal when it is in a combination of aluminium, diethyl aluminium compounds. So, in search of finding out which particular transition metal is giving us this kind of termination of phosphor process, so they ended up having a titanium tetrachloride kind of system, which is producing the high density polyethylene at extremely low pressures and temperatures condition. And the product that we are getting is polyethylene, which is a high density polyethylene, which is linear molecule, and it's also having a molecular mass of 10 to the power 4 to 10 to the power 5. If there is any doubt, please feel free to ask or put your question in the chat box before moving further. So this kind of process is also known as, this process itself is known as Mullen normal pressure polyethylene process. So this normal pressure reaction conditions that comes under this process. Another point is, so from this particular combination, we could also get surface alkylated beta titanium trichloride catalyst, which has been obtained from the combination of titanium tetrachloride and diethylene aluminum chloride. And one more important process which comes under the filler process. So for obtaining, generally we are having a very long chain. So for obtaining lower molecular weight, what we can do, we can add the hydrogen. So hydrogen molecule was added to control the polymer chain length. This is also very, very important step. Like what you will add to control your polymer chain length, you just hydrogenate it. You add the hydrogen and it would control your polymer chain. So coming to what are the advantages and disadvantages, and or I would say the limitations of Ziegler Natta tactics. So we should be knowing that what are the features that we are looking into. So the features are nothing but your low pressure, which is 1 bar. Earlier we were using 100 bars. Second is your low temperature, that's room temperature condition we are using. Third, it is producing high density polyethylene as your product. And fourth, they are linear chains. There is no branching. Right? So now highlighting in red, which is the limitations. So limitations is, since this TiCl4 in a combination of EtAl2HCl, this combination is your heterogeneous over here. So it would be having more number of sites because we are talking about the surface phenomena. So there would be a lot of active sites present. And because of the active sites present over here, what happens? What happens? We get, because of multi-site catalysis as seen in heterogeneous systems, a broad distribution of polymer molar mass, for which we have seen ranging from 10 to the power 4 to 10 to the power 5 dpi, is obtained. So this is a disadvantage because we have a multi-site catalysis happening over there, so we cannot control the activity. So what we can do to overcome this, single site catalyst should be developed. Okay, all right. So this is what we have understood. So before moving to what we were talking about, the single site catalyst have to be developed. We should first know what are the different classifications of your polypropylene. So why are we considering this one? Because when we are talking about Ziegler-Natta, Ziegler was the one who gave CH2 to this high density polyethylene, whereas Natta was the one who used the propene to give polypropylene. Okay, that's why we are interested in talking about the polypropylene classification because we have already talked about the polyethylene. So the conditions here is nothing but the catalyst remains the same, which is your TiCl4 ALET to Cl. Conditions are 25 degrees and 1 bar. Here also it's the same TiCl4 EP2 AlCl. The conditions are same. So here it follows the radical mechanism and it gives the low molecular weight points. Okay, now we are talking about the main thing, which is your classification. So polypropylene has been classified into 5 categories, which is IPP, SPP, ST, PP. PP stands for your polypropylene. Then HIPP, and the last one is your AP. So this stands for isotactic. This is symbiotic. This is your stereo block. This is your hemi-isotactic. And this is your ATAC, right? So these are the different 5 types that we have in hand. So we will take one by one. So the first one that we have is IPP, which is if I am taking a chain. Okay. So if all the methylene molecules, the methyl molecules are facing at one direction, the direction that I'm showing here is this side, highlighted in orange color. This is your CH3. So here, everything or all the carbon atoms, they have same configuration. Their stereochemistry is same. They all are facing at one direction. That is called as IPP. Second type that we have is SPP, which is syntactic, where again the same length 7 number I'm making, and here it is coming like one above, one down. It's wedge and dash form, and again it is reflected as. So I am just reflecting in this different color, so you will be able to see that now it is having a different direction. So here it's a regular alteration of the configuration. So one is down or above or below the plane. So that is called as regular, but alteration of it. Not all of them are facing towards one direction. Moving ahead, we have third type, which is your STPP, which is stereo block. And in stereo block, again, if I am making the same number of the carbon, and here I am having some this particular number above and 4 below the plane, and highlighting it with these dots are just to define your direction, having no other meaning. So it's having a pattern, but it's not that regular. So here the alteration of isotactic C4 to C10 chain blocks with different configuration. Right. So say for example, if I have first three in one configuration, other fours are different configurations. So this comes under a stereo block. Now moving towards your fourth type. Fourth type is hemi isotactic polypropylene, where again if I'm making the same number of chain and one is above, second we don't know, then above, don't know. This curvy nature, we don't know the stereochemistry of it. So the ones which we don't know the stereochemistry of, I am highlighting it with green. So here if I'll just mark it 1, 2, 3, 4, 5, 6 and 7. If you will see carefully, 1, 3, 5 and 7, they appear to us isotactic, whereas 2, 4, 6, they don't have a specific form. No stereochemistry is confirmed, so they are called as atactic. Right? So these are the stereo centers. And the last type that what we have mentioned here is your atactic polypropylene. And here, since the stereochemistry is not defined, it's not regular, any trend it's following. So for example, the first one is above and other two are like this way, we don't know. Then like this, and any random trend is there. That's why in this particular case, I'm highlighting it with green, where it is not showing any particular symmetry. Okay. So this is your irregular statistical change in computation. No regularity is there. That's why it is called as ADAC. So these are the 5 types of your polypropylene that we have talked about. One is IPP, where all the atoms are having same configuration. If they are facing above, that means they have been highlighted as orange. If they're facing down, then they are highlighted as red, which is regular alteration in syntactic. But if we are having certain blocks, certain blocks with one configuration, other blocks is having one configuration, that is called as stereo block. And if they are going as an alternate one, the odd numbers are going as isotactic, other are going as atactic, that is called as hemi-isotactic thing. And lastly, we have a atactic where nothing is regular, any random trend is being followed. So that's why it comes under a atactic thing. I hope this is clear now. So general features, the points that we need to keep in mind. So these stereoisomers of polypropylene, they actually differ in their physical properties. And because of the changes in the physical properties, they have different applications. Say, for example, by physical properties, if I talk about their crystallinity, so the isotactic and symbiotic, they are usually crystalline in nature, owing to their helical structure. Whereas atactic polypropylene, that is amorphous in nature. So because of that, if you have different features physically, then your applications become different. Somewhere we need a crystal molecule, somewhere we need an amorphous, so their applications and requirements become different. So continuing with that, we have seen the different types of polypropylene based on kind of branching it is happening in the stereochemistry they are following. There is a question that generally we have seen that Ziegler-Natta catalyst produce isotactic polypropylene. Why? So the answer actually lies in the fact that always a free coordination. If you see the mechanism, we need a free coordination site which is cis to your titanium carbon bond, and that is extremely crucial for having this kind of isotactic nature. What we are trying to say over here, we need to see the mechanism. So we are taking this titanium, it's having Cl, Cl, another Cl, and fourth Cl. And here it is having this CH3 and CH2, and other way it is connected with CH2, CH, continuing over there. And once this is inserted, this would form titanium, CH2, CH, CH3, CH2, and rest of the things are almost same. And ultimately, what it would form, it would give you titanium, chlorine, chlorine, there is chlorine, this is chlorine. It forms CH2, CH, CH3 facing above, then CH2, CH, CH3 facing above, and it continues in a long chain polymer, and it would create a vacuum site over here. So if you'll see, all the methyl groups are facing towards upward direction. That's why it is your isotactic polypropylene molecule. So this is the reason that always this titanium carbon bond and the vacant coordination is has to be cis to each other. So this is cis. So that influences your attack and insertion of your another alkene molecule uh, in isotectic form, right? Now, moving ahead, we are going to talk about, as I said, we have talked about the limitations of Ziegler-Natta catalyst was that even though it produces the high density polyethylene, but there's a very broad range of molecular mass, which is because of the multi-site activity. So to control that, what we need is we need single site catalyst. Therefore, in that regard, we have single site Ziegler-Natta catalyst. So in this particular case, we have titanium impedance. Here also it is in plus for oxidation state. This is -1, this is -1. Therefore, it's +4. And a combination of, so earlier the combination was TiCl4 and E2AlCl. This was conventional Ziegler-Natta. And this is your homogeneous system. So there is a difference because the chlorine has been replaced with the C2 group. So this particular system being given by the CP2, Ti, Cl2, being given by Nata in 1957. So this is the first ever single site homogeneous Ziegler-Natta catalyst and using for ethylene polymerization. So we have already seen advantages is firstly it is single site and homogeneous. But limitations are also there. The limitations is because of the single site, they are having more activity for ethylene polymerization. Also, it could not polymerize alpha olefins. So these are the limitations that we are having. So keeping this in mind, so keeping that in mind, the limitation, In 1980, another scientist reported high activity by using MAO, which is methyl alumino oxide, instead of your Et2AlCl. So, followed by this, we got zirconium Et2 methyl in a combination of MAO. This particular catalyst that produced around 500 kilograms of polyethylene per mole of your zirconium catalyst per hour. This is a huge amount that has been produced for the very first time using a homogeneous catalyst system, where we have replaced that Et2AlCl with methyl alumino oxide. So we can realize the advantages that we are having with it. So it actually increased the amount what we were getting from the heterogeneous thing, and also this was moderately active for the alpha olefins as well. So in general, we can say that we can summarize the polyethylene and polypropylene catalyst development. So the very first that we have in hand is when we have taken N molecules of CH2, that is your ethylene molecule, and you are using TiCl whole 4 AlEt2Cl 25 degrees Celsius 1 bar. This is your Ziegler-Natta catalyst and has given high density polyethylene with molecular mass range as 10 to the power 4 to 6 dpi. So this is purely a heterogeneous catalysis. Followed by we have second as when we are taking propene and using same TiCl whole 4 Et2AlCl, and it is giving us isotactic polypropylene. This is again a heterogeneous catalysis, and here it is having head to tail linkages. Moving ahead, then we found the homogeneous Cp2 titanium Cl2 with a combination of, this is being found by Natta. This was a homogeneous catalyst for polyethylene. Only the limitation was it was having lower activity and no activity for alpha olefins. Okay, so in extension of this, to extend the activity of it, then we have fourth one, where the titanium was replaced by zirconium and fluorines by methyl group using MAO also. So this actually produces polyethylene, and it showed higher activity for power polyethylene. That means around 500 kgs per mole of your catalyst per hour, which is a huge amount. And also it is moderate, it shows moderate activity for alpha olefins polymerization as well. So this was another feature that we got from the single site. So the main feature it is homogeneous in nature. And the last one that we have got into hand, which has given us even more higher amount, was again using CP2 TiPH2. So it is replaced by that methyl groups of zirconium replaced by phenyl groups, combination of MaO plus zirconium complex combination. So this is a homogeneous catalyst which has reported the highest activity, and the activity is nothing but the 43,000 kilograms of polypropylene per mole of your zirconium per hour. So this has been known to be giving the best ever results for polypropylene. So we have realized that the activity has actually increased when we have introduced the MAO. So what is the role of MAO, which is nothing but your methyl alumino oxide? So if you will see its structure, it is actually like this way, right? So it's having a methyl group over here and it's a chain. So it acts as a methylating agent. So if you have to methylate it, anything, you can use it. Second, it does use acidic carbanion acceptor, acts as, and it results into counter anion to reinforcing cation interaction. What we meant to say is, so if we have this CP2, zirconium, Cl, and Cl, and we are now using Al, MeO. This is MaO. And what will happen? These will be replaced by the methyl group because it is a methylating agent. CP2, zirconium. Now it's methyl and it's methyl. Now when we are introducing it again, what it will do? It will take one methyl from here and it will form Al, MeO, and another. This Me is coming from here and it continues. And it would then make or create a vacant site at zirconium, and here it is methyl with a positive charge. So it creates a vacant site as well as a positive charge. Now when we introduce the propylene, it will then get interacted with it, and here it's methyl, and outside here it is MaO minus because it has taken that one. So this is positive, this is cation, and this is anion, and how MaO is helping in having the interaction between them. And continuingly, if we have this particular system, we will produce isocyclic polypropylene, where we found that this methyl MaO negative, this is acting as a non-coordinating anion with a very low charge density. So it is only helping in interaction between the cation and the anion, and to increase the rate of the formation of isotactic polypropylene. One more example that we can take into picture is if we have CP2 Me2, which has already been alkylated, and now I'm using an US acid, which is a boron compound. So this is your US acid. So what it will do, it will have CH3 here, and because one CH3 can go to that place, so this CH3 will connect to your boron, making it negatively charged, and this is your positively charged. So therefore, this cation ion type of complex, it enhances the uh, activity as well as it can be easily characterized. So it can be easily characterized. That's why the single site catalyst activity is very, very important. So with that, we have taken all the concepts that have been uh, taught by the professor in detail in this particular week. So I hope you guys have understood whatever we have read. Now we will quickly take up the questions of for today and use this concept. So we have first is polymerization of the propylene using the Ziegler-Natta catalyst. We already know that Ziegler-Natta catalyst that produces your isotactic polypropylene, which is having a regular stereochemistry. So out of all the options, it is not highly branched, it's only having a branching of methyl groups, and it is nothing but your stereo regular polypropylene. Now, it has been asked the products of the given reaction, which is TiC3, it's a propene, and we are using again a Ziegler-Natta catalyst. It will give you an isotactic that we have already seen. Now, the polypropylene bearing all the carbon chains of random chirality. When we know that chirality is not fixed, say for example this way. So one facing above, other we don't know, and it is not forming any trend. So this is irregular, or we can say it's random. Therefore, it is called as atactic, right? Now, the statement that is correct about hemi-isotactic. So we have already seen hemi-isotactic, how it looks like. So hemi-isotactic is having this. So 1, 2, 3, 4, 5, 6, and 7. If you will see 1, 3, 6, 5, and 7, that is having 1, 3, 5, and 7. This is your isotactic. And 2, 4, 6, they are having the parallel carbon atoms, which are atactic. So this is the picture of your hemi-isotactic polypropylene. Now, the catalyst variant used by Union Carbide Company for Phillips process for the production of HDPE. This we have taken last time also. It's chromium with 2 CP. In the Phillips process, the HDPE production, the chain length can be controlled. We know that chain length can only be controlled when we are adding the hydrogen to stop that one. So the controlled addition of hydrogen will stop that reaction. Unipol process that was developed by, out of all the options, this is also very straightforward. It is being developed at Union Carbide. And in the Phillips process, the polyethylene polymerization actually happens in the liquid phase. The last question, the Polymers produced in the ethylene polymerization using Ziegler-Natta is nothing but your high density polyethylene ranging from 10 to the power 4 to 6 dpi, and it's completely a heterogeneous catalysis. So with that, our session for today is finished. If you feel any doubt in any point of time, please feel free to ask questions so that I'll be knowing you know or you understood everything, or any other question from previous sessions also. If you have any doubt, please feel free to ask. Thank you. So these PDFs and the study materials will be shared in the same link. So you can just go back and watch the videos again on the YouTube channel. So good evening. Those who are joined now, the session has already started and completed at 6 p.m. So if you have any doubt, you can just put your question in the chat box. So I'll just give you a brief who have joined late. So in this particular week 10 live session, we have covered these topics which have been written on, you can see it on your screen. First one was the offer process, the reaction, nickel effect. We introduced the Ziegler-Natta catalyst. Then we talked about normal pressure polyethylene process, followed by we saw the polypropylene classification as we have seen the polyethylene classification, followed by we have seen the single site Ziegler-Natta catalyst and the brief summary of it. So the offer reaction that we have talked about, it's using this aluminium ethylene compound. And when it is being treated with N-1 moles of your ethylene, it will produce this long chain aliphatic compounds under this high reaction conditions, which is having a 90 to 100 degrees temperature and 100 bars of pressure. Corresponding to that, we have seen that whenever we are having a beta hydrogen, it will eliminate, it undergoes beta hydride elimination, and it gives you side product of this aluminum hydride and this propene system or any chain wherever you are having a R group. So during this process, Ziegler was the one who observed that why it is happening when we are taking the two molecules of ethylene, it is stopping at one butane molecule. That means it is getting dimerization. It is undergoing dimerization. That is because of the impact of the nickel. That is a transition metal. And in presence of the nickel impurities, it is stopping and it is not giving us the desired product. It is giving us a in between or partially done polymerization. So because of that, that becomes a source of the invention of Ziegler-Natta catalyst, where we could design uh, a method where we can have a ethylene to polyethylene molecule. So the catalyst is nothing but the introduction of your titanium tetrachloride with the combination of diethylene aluminum chloride, and it gives you high density polyethylene. We have already seen that uh, polyethylenes are also having 2 to 3 different classifications, whereas high density, low density, so on and so forth. And one more advantage of this particular catalyst was that we were able to get the polyethylene at extremely low or mild pressure and temperature conditions. If you see, the pressures were earlier 100 bars, here it is only 1 bar, and the temperature is also its room temperature. So this is very, very useful. Now, if we will talk about the advantages and the disadvantages of the Ziegler-Natta catalyst, Ziegler-Natta catalyst is giving us the high density polyethylene, which is actually being used in a lot of purposes. And the advantages that it is having is it is using or it is doing the reaction at an extremely low pressure of 1 bar, low temperatures, that means room temperature itself it can produce the polyethylene. Also, the product that we are getting is high density, not the low density one. And we are getting extremely linear chains. There is no branching. But on the other hand, if we'll talk about the limitations of it, since it is using a heterogeneous system, so in heterogeneous, we know that it's a surface phenomena. And in surface, we'll be having a lot of active sites. Whenever we have a lot of active sites, there we cannot control the molar mass. That would be a broad distribution of the molar mass, and therefore there is a need to introduce a single site. There should only be one particular titanium which could actively participate in giving you a particular product. So we will take up that in later time. So what happened? Ziegler introduced the polyethylene formation from the ethylene using these conditions, and Nata, which is the second partner who uh, produce the polypropylene using a propene under the same conditions. But when I'm talking about the polypropylene, there are different classifications of polypropylene that we have in nature. Earlier, we have already in last sessions, we have already talked about different classifications of the polyethylene. Now we are talking about the polypropylene. So polypropylene is classified into 5 different categories. One is isotectic, second is syntactic, then stereo block polypropylene, hemi-isotectic and atectic. They're very easy to be understood. So let's take the picture one by one. When we are talking about the isotectic, these all polymers, they are based or classified on their stereochemistry. Stereochemistry means that how their groups are arranged in the space. So if you'll see, if I'm talking about the polypropylene, there is a methyl group only present over here. So these methyl groups, when they are approaching or they are directing towards one direction, say for example, if I'm showing in this particular direction, so that is having all the carbon atoms all are having same configuration. That's why it is known as iso. Iso means same. So they are the most crystalline in nature because they are following a certain trend. Whereas if we have a certain pattern like alternative form, one is up, one is down, or one is below and one is above, that is called when we are having an alternative stereochemistry, which comes under your symbiotic. So this is the second type. So both of them are crystalline because they're following a certain order of their pattern. There is a pattern over there. When I'm saying that first three carbons are having above symmetry and other fours are having down symmetry. So there is an alteration, but there is a block system. Like one block would follow one symmetry and one block would follow another stereochemistry. So this is called as stereo block polypropylene. Followed by we have a hemi-isotectic. Hemi means it is not fully isotectic. If you see first carbon, third carbon, fifth carbon, and seventh carbon, they're following the same trend. The carbon number 2, 4, and 6. If you see this zigzag, zigzag means there is no defined stereochemistry. When I'm talking about either wedge shape and the dash shape, this is above the plane, this is below the plane. But when I'm giving a curvy nature, that means its stereochemistry is non-proven. So only the carbon number 5, 3, 1, 3, 5, and 7, they are having a defined stereochemistry which is having upward direction. So it is called as isotectic. And 246 stereo centers, they are atectic because they are not having a regular or defined stereochemistry. So that kind of combination is known as hemi-isotectic. And the last combination that we have is atectic, where if you will see, first one is above, second, third we don't know, then fourth one is there, fifth one stereochemistry we don't know. So there is irregular trend. That's why it was called as atectic polypropylene. So point that we need to be noting over here that all the stereoisomers that we have talked about of polypropylene, they differ in their physical properties. We have already seen what is crystallinity in nature. Whenever there is a regular trend for a longer time, we have a one unit over here, at certain distance another unit here, at certain distance another unit here. So it's a repeating unit with a certain pattern. So periodic nature is there. That's why we call it as a crystalline. When they're randomly orienting or arranged, that is called as an amorphous nature. So we have that we got to know that isotectic and syntactic, they are crystalline in nature. But in case of the APP, that is atactic, that is amorphous because we saw no regular trend over there. So based on that classification, we got to know that the physical properties are different. That's why their usage and their applications would also be different. So why were we talking about this one? Because Ziegler-Natta catalyst is one, which is titanium Cl4 Et2AlCl. This catalyst will give you only the isotechnic polypropylene. That means all the methyl groups would be having a head to tail linkage. Why it is happening? Because if you'll see the mechanism, so this is a general chain or titanium tetrachloride. And when we are introducing the propene group over here, firstly it will insert and coordinate and it would form certain four-membered kind of ring over here. And if you will see, it would continue to form CH2, CH, CH3 is above. Then this is a bond between CH and CH2, again CH and facing CH3 above direction. When all the CH3s are facing above direction, that is called as isotectic. And if you will see the vacancy of the titanium, where the other alkene molecule can come and bind, that is cis to your already formed polymer. So it is said that a free coordination site, which is cis to titanium carbon bond, that is very, very crucial to give you the isotactic polypropylene kind of molecule. So this is the reason why we are getting only the isotactic and not other features. Followed by, we have already talked about what are the disadvantages that are related with the Ziegler-Natta. Even though their activity is high, but still we say that there is a limitation. What is the limitation? That because of there are too many sites, like if I'm talking about this surface and this surface is having one titanium here, other here, here and here. So multi-sites are there, and because of the multi-sites, we cannot control their molar mass. So for controlling their molar mass, we need to have a single site catalyst. So how can we have a single site catalyst? Single site means homogeneous group we are talking about. There is only one center which is having a certain oxidation state, and that is going to be actively participating in carrying out the reaction. So in that particular aspect, Ziegler-Natta introduced this titanium-based catalyst. Earlier we were having TiCl4. Now the two Cls have been replaced by the Cp rings, and that has made its um, catalysis as a homogeneous, whereas there would only be a one titanium center. So this particular catalyst was the first ever single site homogeneous Ziegler-Natta catalyst for the ethylene polymerization. Advantages we got to know that we can control the molar mass. There is a single site, but the limitation is because it is single site, we can't have a higher activity, and it is limited not to polymerize any alpha olefins that we have already covered in previous sessions. So to have so to enhance the activity of it, what has been done? Another scientist uh, Okay. Another scientist has reported higher activity using the homogeneous catalyst using this MAO. So earlier we were using TICP whole 2 Cl2 and ETAL2Cl, right? So this was having limited activity. Now when this has been replaced by this MAO and this has been replaced by a zirconium kind of catalyst, their activity has been tremendously increased by producing the 500 kilograms of polyethylene molecule. Similarly, if we just summarize what are the different catalysts that have been developed for polyethylene as well as polypropylene. So we'll start with the heterogeneous systems where if we are taking in n moles of ethylene molecule, it would give you high density polyethylene molecule by using the titanium Cl4 as the Ziegler-Natta catalyst. Remembering it is a heterogeneous system and we cannot control its activity. It's very, very highly active. Secondly, if I'm taking a propene, it would give you a polypropylene. And we know that what it gives us an isotactic. All the methyl groups are facing upwards. So it is having a regular trend and it is crystalline in nature. So this comes under your heterogeneous catalysis again. Now to control their molar mass, they have introduced a homogeneous catalyst where they replace the 2Cl of the TiCl4 by Cp groups, and they could easily see that it's a homogeneous system, but the limitation is the lower activity as well as no activity for the alpha olefins over there. Moving ahead to increase the activity of it, they introduced the MAO, which is methyl alumino oxide. And this particular catalyst over there, they could see that there is a tremendous increase in the production of the polyethylene per mole of the catalyst in per hour. And there is also having a moderate activity for the alpha olefins. And lastly, when they have even more changed the catalyst with from the zirconium to titanium having CP2 and PH2, with a combination of zirconium catalyst, they could produce from 500 to 43,000 kg of your polypropylene per mole of the zirconium in per hour. So now why do we have to understand the MAO role? Because earlier we were not using the methyl alumino oxide. Here we are using, so it is having three particular features. Firstly, it is a methylating agent. It can replace your fluoride of your catalyst by methyls. Also, it introduces a Lewis acidic carbonyl acceptor kind of character, and it increases the interaction between a counter anion and the zirconium cation. We will see in a bit. So if we have this particular zirconium Cp2Cl2 catalyst, and we are using an MAO. This methylating agent can take up the chloride and methyl can come over here, and this becomes highly electronically rich over here. Now, when we are introducing another molecule, this Me can be easily be taken by your polymer, this AMAO, forming a chain as a negative ion, and this would become an empty space. So when that methyl is gone, it introduces a cation over here, also a vacant site. This vacant site is needed for introducing your alkene system. Once it is being interacted, and then we have a cation interaction. Because of these systems only, we could increase the activity and the production of it, which would ultimately give you isotactic polypropylene. where we got to know that any the methyl that it has taken that forms an anion, and that is a non-coordinating. This anion is not coordinating to your zirconia. It is just having a low charge density to balance the reaction and to increase the reactivity over here. And to talked about the reduced acidic nature that I was talking about, how it's introduced. So as in when we have used an MAO, it has made this methyl version. And because of this methyl version, we are having a Lewis acid in nature. Lewis acid boron moiety will readily take up this methyl because it is having empty orbital. And since the interaction is more towards this side, this becomes negatively charged and the zirconium gets positive charge, and this leads to your desired product. So this can be easily characterized, and therefore the single site activity becomes highly important to control what kind of product you want and what kind of structure you want. So once this was over, we have just seen the assignment questions. So these questions are nothing but just an examples how you have to solve your assignment for week 10. So the question says that polymerization of propylene using the Ziegler-Natta catalyst produces what? So we have already seen that it produces a polypropylene where all the methyl groups are facing upwards. That means a regular trend has been formed. So out of all the options, the stereo regular polypropylene that was formed, that is an isotactic. The second question is similar, that it's the same catalyst and it is asking like what would be the product of it. It's an isotactic. So third question, when we are having a polypropylene, which is having a chain carbon atoms of random chirality, we don't know the chirality of a certain pattern that is corresponding to have an A tactic. So already I've introduced, so you can just go back and check the slides and watch the videos again. Another question regarding the polypropylene is hemi-isotactic. What kind of stereoisomers or the chiral isomers it would be having? So 1, 3, 5, and 7 position could be a chiral which is isotactic in nature. Others are having no uh, known stereochemistry. So they are called as atactic, and that comes under hemi-isotactic nature. Followed by this has been covered in last session where Philip process where we are terminating the chain length by introducing the hydrogen, and that uses the chromosine over there, CP2 chromium. And the next question also, it is corresponding to that only. When we have to terminate the length of our high density polyethylene, we just hydrogenate it or we introduce the hydrogen molecule. So controlled addition of the hydrogen will control your chain length. Unipole process, same thing that has been developed at Union Carbide, and the Philip process where the polyethylene polymerization happens. So it is asking about the medium of the reaction, whether it's solid phase, whether it's liquid phase, whether it's a gaseous phase. So it is actually a liquid phase. And the last question that we have is polymers that produce in the ethylene polymerization using the Ziegler-Natta, whether it is 1-butene, LLD, linear low density polyethylene, high density polyethylene, or low density. It is actually the high density polyethylene. That's why we have gone towards the single site catalyst. So I hope you have understood. If there is any question, please let me know. Within 5 minutes, we'll be ending up our session. So is there any question or doubt? You can unmute yourself and ask, or you can just put your question in the chat box. Okay, so if there is no question, then I would thank you for joining the session, and we will meet in next week, Saturday. Please remember the timings of the session. The lecture starts at 6 p.m. sharply. So if you guys are joining in between of it, it is very hard to go back again and then to revise the thing. It is better to save the time also. Please join at 6 p.m. Next Saturday. I'll see you guys there. Thank you for joining.